right regime. Here we go. Okay, fantastic. So good morning, everybody, and sort of welcome to the next lecture in the series. So today we are going to talk about the deep kernel learning. So which is essentially how we can combine the variational autoencoders capability to simplify and find the relevant traits in data with the active learning by the Gaussian processes. So just as the quick rehash, in the first several lectures, we talked about simple Gaussian processes. We talked about what the kernel and the kernel parameters are. We talked about the kernel priors and noise priors and why they matter once you set up the Gaussian process. We talked about the min function and the priors on the min function that gave us the structured Gaussian process. We talked that once you have the Gaussian process with priors and the experimental data that allows you to go from priors to posteriors, and posteriors allow us to give the prediction of the function and its uncertainty. And then we discussed how we can use the predictions and uncertainties in order to construct our exploration strategies. So notice again that the Gaussian process and Bayesian optimization is not the same thing. One is the way to interpolate and get uncertainty. Another is to somehow combine this prediction and uncertainty in order to guide the active exploration process. So we looked at basically the framework for the simple GP and the Bayesian inference. So we have the measurement, we have the ground truth function. So this is our comparison. We never have an access to the ground truth in the real experiment. We have some measurement points. So using the measurement point, Gaussian process creates the surrogate model and the uncertainty. And in many cases, the uncertainty allows us to actually guide the exploration of the space. Not always. So we can have a very large difference between the surrogate model and the actual prediction, and the uncertainty here can be small. So sometimes the Gaussian process can be certain, but incorrect. Nonetheless, most of the time it is not the case, and that's how the Bayesian optimization works. So we talked about the fact that the Gaussian process is purely data-driven. This is, if you will, the paradigmatic big data method. We talked about Bayesian inference, so this is a different approach. In this case, we have some model and some idea of parameters at the priors, and then we update the parameters. And structured Gaussian process kind of combined the Gaussian process and Bayesian inference by creating a physics device min function. So for acquisition functions, we basically looked at the basics, saying that there are prediction, what we think will happen. There is a estimated risk, what we think the uncertainty of what will happen. There are multiple ways how this prediction and uncertainty can be combined to guide our exploration. So in other words, acquisition function is how we make decision based on the prediction over the whole parameter space and on the uncertainty over the whole parameter space. These are usually coming with the specific names. So the tried and true are upper confidence bound, probability of improvement, expected improvement. Important thing is that there are always more. Another very, very important message is that the acquisition function is not a mysterious mathematical object that we don't quite understand. So acquisition function is in fact something that takes into account or can take into account the real cost of measurements. So it can vary depending on where we are in the parameter space. It can come from a different Gaussian process that learns the costs as opposed to learn the benefits. So of all the things that you are most likely going to start tweaking with, acquisition function is probably the first one. And it's actually very simple if you think about it. And then we looked at the standard Bayesian optimization when we basically have the cycle when we do measurements on two locations, reconstruct the function and the uncertainty, calculate the acquisition function. So the measurement is taken at the point of the argmax of the acquisition function. So this is in some sense our way to balance the prediction and uncertainty inside. And then if we take the next measurement and retrain the model, that becomes our Bayesian optimization loop. So I've shown you how we can use the Bayesian optimization for a simple Ising model, where this is the ground truth, this is the exploration using very greedy algorithm, and this is how the prediction look like. So these are relatively simple and have been covered at some length in the first several lectures. However, we also discussed the limitations of the classical Gaussian processes and Bayesian optimization. So notice that these topics are the area of the continuous debate. So there are still papers coming out where people argue that Gaussian process works in any dimension. That was not our observation, but keep in mind that there is a less discussion about Gaussian processes that there is about the large language models. But generally, this topic picks up big time because using LLMs in the practical labs for the time being is either very difficult or not an option, whereas the GP and BO becomes a part of the work and progressively increasing number of labs. In the last several years, the progress has been absolutely amazing. So nonetheless, generally GP doesn't work very well other than in low dimensional spaces. We have to deal with the fact that correlations are defined by the kernel function, which can be exceptionally limiting. We don't use any knowledge about the physics of the system. We don't use any cheap information available during the experiment like proxies. Correspondingly, structural Gaussian processes actually address this part. In next week, we are going to talk about in the last lecture, actually, we are going to talk about how the proxies work and how to incorporate them in the multi-fidelity Gaussian processes. So today, we are going to, today and on next Monday, we are going to talk about how to extend Gaussian processes to the high dimensional spaces. So what are the motivation for that? So the motivation is that very often we want to learn something like structure property relationship. For example, the relationship between the structure of the molecule and its properties. So property is usually a scalar, like boiling temperature, enthalpy, dipole moment, whatever. Structure is obviously a very high dimensional space, a high dimensional descriptor. So molecular structures are high dimensional, and more importantly, they're living in the non-differentiable large dimensional space. The second topic where it appears is molecular discovery and the quantitative structure activity structure relationship, QSR. So this is a very similar problem. Third example is processing optimization. For example, if you choose the method to anneal the film or make material or charge the battery, that's where it's coming from. So let's look at a few examples. So one example is making steel, right? So people have been making steel for millennia. The know-how of how to make the steel with a dedicated infrastructure like a Damascus steel or Woods or the Bulat steel in Russia, that's a kind of big secret. And it turns out that if you want to make a good steel, you need to control the composition. So, of course, you have the basic phase diagram of the iron and carbon, but practically what matters is the role of the additives like chrome, nickel, and so on and so forth. But the second part of it is the processing. So this is the example which I found somewhere on the internet, how we make the steel of the certain composition, so how we anneal it. So it's a pretty complicated process. And finding out and discovering these parameters manually, just by trial and error, is not a very simple problem. So in fact, that's actually an interesting historical example that in India and Syria, when the Damascus steel was created, the discovery was probably accidentally. Who knows how long it took. So the way that Damascus steel was rediscovered in 19th century by Mosov in Russia, that one was actually based on the analysis of the microstructures and analyzing what are the mechanism behind the steel structure formation. But anyway, so let's assume that we don't look at the mechanism, so we just want to optimize the steel, and we need to discover this type of trajectory. And if this temperature is higher or this temperature is different, things don't work nearly as well. Another example is the battery charging. So currently we are used to the fact that if we have the phone, we can plug it and it can be fast charged in several tens of minutes. We know that in some sense, feasibility of the electrical vehicles depends on how long they will take to charge, because we are used to the fact that we can fill the car at the gas station in 5 minutes. Obviously, for electric vehicles, that's a concern. So we do know that we can always charge the battery faster if we apply a higher bias. The problem is that if we do that, then if we cross certain barrier, then the battery will start to electroplate lithium. Once it happens, the battery basically is not your friend anymore. So whereas the burning gasoline can be extinguished, burning battery cannot be extinguished. It will burn until it is done. Correspondingly, obviously the details of the battery charging is probably closely held trade secrets of Tesla or the electronics manufacturer. But the general principle is that if you want to charge the battery, you actually start with the fixed. So this is the kind of active voltage. So you start with the fixed voltage charging, and then you kind of explore how fast it charges. Then once you reach the threshold voltage, you start to make it current galvanostatic, and then decrease the charging current start to decrease. So it's a complicated two-step process. In order to optimize the battery charging, people have come up with a more complex kind of processes. But again, the question becomes, how do we do it systematically? So how can we find what is the best charging trajectory? And of course, problems like this appear in the manufacturing all the time. For example, if we want to anneal hybrid perovskite in film for solar battery, we need to find the right conditions for materials so it forms the microstructures that are beneficial for, which are crystalline enough to avoid the traps, but at the same time avoid the formation of the second phases. And then goes on and on. Pauling ferroelectrics, sort of choose your preference. So the optimization of the process trajectories is the example of the typical optimization in the high dimensional space. So how are we going to do that? So let me illustrate this using the same example of the ferrocene model that we discussed in the end of the last lecture. So basically what this model is the hybrid of the lattice model and the Ginzburg-Landau model. Practically what matters is that we can use this model and simulate how the polarization will respond to the external electric field. So for example, if we switch the electric field like this, then the spins inside the model will, inside the grid will switch like this, imitating the ferroelectric switching. The nature of the model is such that depending on, we can control the tuning, coupling between the the spins, and get the idea of how the hysteresis loops look like. So for the purpose of this discussion, the only thing that we need to know is that we can send the electric field to the model, and we can calculate the responses that have the form of this hysteresis loops. So that's all we need to know. Question becomes, how can we, by the way, for things like battery charging, by now there are super useful models like PyBAM that allows us to simulate the charging of the battery by providing the voltage as the function of time. So by now, the number of easily accessible models of the complex phenomenon is kind of extreme. Now, the question becomes, how can we optimize the system? So the simplest way to do that is simply parameterize the process by a small number of variables. So for example, if I want to have this hysteresis loop, the one natural variable can be the amplitude of the applied bias. Another can be, for example, the coupling inside the model. And in this case, I can simply calculate the properties like hysteresis loop area or the asymmetry using the grid. So I said that I have two parameters. With the two parameters, I can calculate the properties of the grid. It works. It's actually very time consuming and very ineffective because we have essentially to calculate the response at each point in the two-dimensional parameter space. Can we do better than grid search? Absolutely. That's exactly for what our simple Gaussian process-based Bayesian optimization is for. So in this case, the workflow becomes relatively straightforward. We start with our numerical model. We start with our calculation. So we calculate, in this case, hysteresis loop. We calculate our target function, for example, area under the loop. And then we say that, you know what, we have the parameter space that we are interested in. And then we simply use Bayesian optimization in order to maximize this target function in this parameter space. If our parameter space is low dimensional and if our target function is scalar, that's actually very straightforward. So that's a simple textbook example of the Bayesian optimization. And we can run it. So that's how it works. This is an example of the our parameter space. This is how the exploration of parameter space progresses from the measurement till the 10 steps, 50 steps, 150, and so on. This is our prediction. This is our uncertainty. Our acquisition function was we want to find the regions at which the loop area adopts certain value. And this acquisition function guided our exploration. And you can see that we found that these regions are sitting on this line, which is exactly something that we can find here. So if I want to find the points where the loop area has some fixed value, you can see that they would be sitting on this type of surfaces. So Gaussian optimization is, or Bayesian optimization is great for this type of stuff, and it's relatively easy to realize. It works. But the problem becomes, what about the trajectories? So I've shown you the example that if we have the complex trajectory, we have the responses that can be maximized at the different part of the field history, and they depend on what has been happening before that. So we cannot necessarily predict, we cannot necessarily describe our process just by two parameters. Sometimes we have to take the full trajectory into account. So in order to deal with this problem, we said that our first approach can be to simply combine the variational autoencoder and Gaussian process. So what happens in this case? We need to come up with the certain number of the plausible trajectories. So these are typically coming from domain expertise or something that is physically makes sense. So how to select them is a kind of domain-specific problem. But generally, we say that we build them based on what makes sense physically, what comes from the domain expertise, and what allows for sufficient variability. So the good thing is that we can create a lot of them. After we have these model trajectories, we send them to the autoencoder. So autoencoder does two things. It learns how to reconstruct the trajectory by itself. It's not particularly useful, but it also forms the latent space. And the latent space is the way to represent the factors in variability and the trajectories sufficiently well and in sufficiently smooth way. So if we choose multiple trajectories, there is initially no logical way to go from one to another. Once we use the autoencoder, they become ordered and in such a way that the factors of variability are identified and disentangled. So the latent space of the variational autoencoder, in this case, becomes a natural playground for us to perform the Bayesian optimization on. So in this case, the way that we do stuff is that we take the point in the latent space, we say that this is our exploration space. We want to run Bayesian optimization in the Latin space. We pick a point, we decode the trajectory, we send this trajectory to our black box model, we get our output, and then we essentially build the relationship between the we run the Bayesian optimization where the parameter space is the low dimensional Latin space, and our function to be optimized is the target functionality. So this part, decoding, running the model, and evaluating target functionality, this becomes our optimization function. And then we proceed as before. We simply compute the acquisition function, and then we run the Bayesian optimization cycle. So we looked at how the VAE will work in this case. So this is the example of the VAE encoding decoding. These are the examples of the trajectories we have chosen. Since in our case, we created the trajectories using some mathematical operations, we can see how the ground truth parameters are distributed in the Latin space. That's not particularly useful, but it gives us the idea about relationship between our examples and the latent variables. Once we start to choose latent space as the generative space, so meaning that we take point here and decode trajectory, take point here and decode the trajectory, and so on. In those cases, we basically sample all latent space uniformly, as opposed to the sampling it according to the latent distribution. For example, here all the trajectories are almost the same. We don't need to sample many of them. Here, they can be not even a part of the original data set. So we kind of create the new ones. I've shown you the example that it was always a good idea to look at the ground truth behavior. So what happens inside the system if you can calculate things on the grid. And we've shown that in this case, the target function is distributed like this over the Latin space. So it's a fairly complex distribution. Nonetheless, Bayesian optimization can actually discover the regions of the interesting behavior. So this is our Latin space with the initial seed points. This is our exploration pathway. These are the regions where our Bayesian optimization clearly converged. So this is the reconstructed curl surface. So this is what the GP gives us. This is the ground truth curl surface. So you can see that we did find the regions where our response is maximal, as we want it to be. That being said, we also discussed the fact that in this case, the target function is actually fairly complicated. So you can see that there are very narrow features here, which basically means that the Gaussian process kernel length has to become small in order to find them well. Now, can we use the structured Gaussian processes to improve the shape of these features? Not really, because we don't have the laws that operate inside the latent space. So we don't have any basis to build the model. So why does it behave this way? Very simple, because the structure of the latent space in the variational autoencoder is determined by the data only and nothing else. So if our input features are correlated with the outputs, we will strongly correlated with the outputs. We will have a well-behaved surface. If these relationships are more intricate, then we're going to have these complex structures. The question becomes, can we do better? So, and this is exactly what we are going to talk about today. And as a first example, let me start with the same card data set that I used for the autoencoders, where we have cards and then we create the objects by rotating and shear. But let's assume that now we treat the cards as the example of the function. So what I mean by that is that we see an object. So this is, let's say that instead of trajectories for the ferrocym or the battery charging, our inputs are objects like this. This is a high dimensional object. What our function will be is to take an object like this and identify which of the suits of the card it is, or identify the rotation, or identify the shear. So in some sense, it's a kind of toy model where we treat the image as the object, and the parameters that were required to generate this image as the function of this object. So it's fairly abstract, but it's exactly the same type of setting as the process optimization, except that for process optimization, it would be a trajectory, and the function would be the properties of the material that you discover that form after it was processed using this trajectory. So I've also shown you how this card behaves in the variational, in the latent space of the autoencoder. So if we take the data only and run it in the VAE, we are going to have the latent distributions like these ones. So ground truth label show you that there is some internal structure. Obviously, it's fairly complicated. So, and we experimented with the normal VA and rotational invariant VA and showed that that one worked better. So now, how are we going to realize our kind of card function? And that's what we are going to do using the deep kernel learning. So as usual, I'm not going to go deep into the details of how it writes, how it operates, and what happens under the hood. But let's look at the basic concept of the deep kernel learning architecture. So the deep kernel learner is combined of essentially two parts. So one part is the network. So this can be a convolutional network, it can be multi-layer perceptron, it doesn't matter. It can be graph network. The only purpose of this part that is shown in green is to take the high-dimensional input object, send it through the set of the neural networks, and reduce dimensionality until we get to this embedding layer. So this embedding layer is equivalent to the latent space of the autoencoder. In fact, autoencoder will appear if from this embedding layer, we start to expand the data back to the original dimensionality. However, the way the deep kernel learning works is that instead of the expanding the embedding layer back to the original dimensionality, we actually use it as the space and define the Gaussian process on top of the space. And this Gaussian process connects our latent space to the target functionality. So in some senses, think about it this way. We have the autoencoder, we cut it in half, and then we transplanted the Gaussian process on top of the latent space. How is it different from the VAE and GP? Very simple. VAE and GP, we train VAE based on the input only, and then we run the GP on the embedding space, and then the embedding space doesn't change. Once you have the deep kernel learning, the whole system is trained from the beginning to the end, meaning that we build the relationship between the target and the inputs, and we train our Gaussian process and our embedding network at the same time. So in this case, the embeddings in the deep kernel learning are dynamic, whereas the embeddings in the VAE are static. So once we train the DKL, the embeddings will change as we chase the target. In VAE, they stay kind of constant, and we just try to explore the fixed latent space. How do we use it? I mean, you have seen this slide already 3 times during the presentation. The reason is that we use the deep kernel learning exactly the same way as we would use the normal Bayesian optimization, except that what it does is that this space stops being the low dimensional parameter space. It becomes the, as you see it, it becomes either the latent space of the DKL that we can sample, but it is what it is, or it is a high dimensional space of the objects over which we want to optimize. So let me show you a few examples. So I can show it on the presentation, but it may be much more illustrative to show it over the to show it using the Colab. So the Colab has been posted on the GitHub, so you're more than welcome to play with it. So it runs from the beginning to the end, so let me know if there are any problems with that. And basically what it will introduce this deep kernel learning using the cars as an example. And as I said, if it works for cards, exactly the same approach will work for process optimization, molecules, and so on. And I'll show you how it works for molecules a little bit later. So this notebook takes a little bit of time to run, so I'm not going to do that, but again, you can experiment. So how does it start? We start with our installation of the our control libraries. So in this case, of the unusual ones, we introduce Cornea and Atom AI. Basically, they are necessary to prepare the data only, so they're not a part of the DKL at all. So then the way the notebook works is that we start with the downloading the data set of the cards. So these are just the images of the cards that we use in order to generate our object. So this is what this GDown and the unzip is doing. So once we have downloaded the images of the card, we can create our training data set. So in this case, this function, transform images, is explained here. So there is nothing special about it. So basically all it does, it takes the images of the cards, normalizes it, defines the transform function, and our transformation becomes some combination of rotations, translations, and shear. So that's all there is to it. And what we are going to do is to create the cards data set and then the ground truth labels. So for each card, we have its ground truth label, its ground truth angle, ground truth translation, and ground truth shear. And these are the parameters. So the angles are changing from minus 120 to 120. Translations are changing from minus 0.1 to 0.1. Shear is 20, whatever units, and we get 2,000 examples. So notice that this is a very strong disorder. So in fact, most of the machine learning algorithms, if we don't make a provision for accounting for the rotations properly, will have a lot of trouble working with the rotated objects. So 120 is a strong disorder. If you want to experiment with this notebook, so try to make this very small. Then we remove one factor of variability. Try to make this smaller and experiment what happens if this is 20 versus whether it is 1 versus what is 120. But in this case, I'm showing the most I make the disorder in the system very, very strong. So what do we do next? We can visualize the card objects. So this is how they look like. So you can see that they're rotated, they're tilted, they can be shifted from the center. That basically gives you an idea of what these parameters will do. And then just to illustrate the point, we can run the variational autoencoder on this. So the way it is realized is through the, so in this case, it is done through the Atom AI autoencoder. So this is by now is very straightforward. So we define the input dimensionality of our data. We say that there are 2 latent variables. We define how many layers are for the encoder and decoder. Then we train it. Lo and behold, we can visualize our latent space. So this is how the latent space look like. It's not super good because this is a strong disorder. So reconstructions are not super good. This is our latent distribution. So this is kind of very similar to what you have seen in the presentation. So we visualize the latent distribution with the ground truth labels. So meaning the suit and the, let's say, shear. So you can choose which of the parameters to use the ground label. In this case, I use shear, but you can use rotation or whatever you want. So this gives us an idea of what is the distribution of the ground truth labels inside the latent space. And of course, if we don't have access to the ground truth, then we would just see the dots. And then it would be up to us to assign some value to the specific group of the dots or introduce the metrics over the specific part of the distribution. So that makes perfect sense. And then, as I mentioned, if we'll run the rotationally invariant VAE, which is realized using the RVAE function, in this case, the distribution is much better. It's still not superb because the disorder is very strong. So a lot of the cards element get mixed. But notice a very interesting thing. So you will actually notice it down the line when we discuss the outputs of the deep kernel learning. So notice that the card label 3 is sitting on the top of this Latin space, card label 0 sitting on the bottom, and then the labels 1 and 2 kind of intermingle with each other. So then you can look at the shears distribution. So you have a disentanglement of the shear effects as much as it can. But overall, it's a fairly complex manifold. So how are we going to use this for the, how are we going to, can we use these cards to illustrate the deep kernel learning? So very simple. So what we want to do is imagine that we use the card as an example to explore the function of how, given the image, we can constrain the hand, or how, given the image, we reconstruct rotation or shear. In other words, we want to train our algorithm, so we give as an input one of these objects. Let me get to this point. One of these objects. And what we wanted to do is to tell us what hand it is. So it's essentially a classifier problem. If we want to say what is the rotation or what is the angle, then it is essentially a regression problem. So we want to identify the parameter of the object. What makes it difficult is that if we want to identify the hand, then we want to identify the hand for all possible rotations present here. If we want to understand the shear or rotation, then we want to do it for all rotations or shears and all hands inside the data set. So how can we do that? So, and let's just see how the deep kernel learning is going to do that. So first thing we're going to do is to define some control variables. So the number of the initial seed points, the number of exploration steps. So this is how many initial examples we take. Exploration points is how long we continue after active learning. And then we need to define the two parameters associated with the batch size, because that allows us to do things fast. So now let's run the experiment when we want to learn the hand, and let's assume that we run it for clubs. So in this case, we define our function in a way that we take card images as the inputs. So this is what this function does. So we start with the dimensionality of the input being equal to 900. So 900 is 30 square. So this is 30 square is simply the size of our flattened card object. Then this is our x. So our target is basically the one-hot encoding, where if the card is clubs, the target is 1. And if the hand is not clubs, then the target is 0. So in some sense, our function is binary. It's 1 if the card is clubs, and if it is 0 if the card is not clubs. So this is this is all it takes to run the code. So we define our random keys. We create our deep kernel learning using variational inference for speed, and then we fit our model. That's all it takes. So the output of the model is going to be fairly simplistic. So it is the key lengths. So there are 2 lengths because our latent space is 2-dimensional. We defined it here. So the input is 900 dimensional object, the card image. The output latent variable is 2-dimensional. This is our latent space. And our kernel over this latent space is the RBF, meaning Gaussian. So these are the parameters of this kernel. This is the scale of this kernel. This is the noise. So now let's do the following thing. So now let's visualize the latent space of the deep kernel learning agent. So it's two-dimensional, similar to VIE, but we are going to visualize it using the handle the card suite as an example. So see what happens. That this is the distribution of the actual labels. So remember that we have 4 actual labels. One is clubs, 3 are everything else. See what happens. That the clubs form a well-isolated cloud in the latent space of the deep kernel learning. 3 other suits form overlapped clouds in the different set of the deep kernel learning. We can look at what happens with the rotations and shear. So remember that for each card, we have the example of the rotation and shear, and they kind of sort of got somewhat, they're not definitely random, but by far and large, they are all mixed together. So what happened is that despite the fact that our algorithm has to work with the data with a very strong disorder, we told it to find the clubs, and it did find the clubs. So this is the ground truth labels. These are the predicted targets where we make clubs 1 and everything else is 0. So our algorithm learned how to separate ones and zeros in the most effective way. So what are we comparing? We are comparing it with the distribution like this. So if we try to form the latent space using the simple variational autoencoder based only on the similarity in data, then our ground truth labels are mixed like that. So if our clubs is whatever number 0, you can see that it's spread throughout. It never mixes with the other hands, but it forms a kind of fairly spaghettified mixture, so that it's strongly interpenetrating distributions. So we will not be able to say, if we didn't have labels, we would not be able to say which ones are clubs. If we run the deep kernel learning, the situation is totally different. In this case, it worked like a charm. It clearly separated them in one part of the latent space and everything else in the other part of the latent space. That's actually pretty impressive. So notice that in this case, when we run this process, we actually run the deep kernel learning on the whole data set. So this was not active learning. This was essentially a supervised learning. So we trained it on the full data set, and then we applied it to the full data set. We didn't kind of test it. We didn't divide it in the test and train tests and validation sets. But if I separated it 50-50, the result wouldn't change. So it actually works remarkably well. We can run the same algorithm also as the active learning. So what's the difference? In active learning, we start with a very small number of the seeds, for example, 10, and then we run the active learning in the usual way. So why does it matter? It matters because if we talk about the cards, I mean, cards are cheap, right? We can create any number of them and the process will work. If we talk about the optimization of the processing, then presumably our inputs are the possible trajectories, and our outputs is actually the measured parameters of the material or battery or whatever. In other words, experiments are expensive. In this case, we use the DKL like we would use a supervised neural network, meaning that we believe that all experiments have been done. So we have the 2000 inputs, input features, and we have 2000 target features. So now let's run the process as an active learning problem where we assume that we start with the 20 seed points. So this is 20 initial experiments that are chosen randomly. And then we run the 100 exploration points. So 100 exploration points means that we we start with our 20 seeds. Then the algorithm tells us what should be the next point. So we run exploration. Then we update model. The algorithm tells us what should be the next experiment after that, and so on and so forth. So this is actually active learning in a sense that the algorithm constantly goes from prediction to run an experiment and then updates the model given the experiment. So how are we going to do that? So this code is relatively straightforward. So what we start with is we choose 10 initial candidates. So this is just a random choice with the size of initial number. Then we take the examples, and then we define the unmeasured objects, where basically unmeasured objects is where we take the measured objects, all objects, and remove the ones that has been used for training. So then we do a little bit of the, then we define the targets for these measurements, and then we set up our exploration loop. So it's actually very straightforward. We create the cycle which has the number of steps equal to number of exploration steps. And then we proceed as before. We train our deep kernel learning model. We fit the model to the training data. We calculate our acquisition function as before. Our acquisition function in this case is we calculate the mean and variance explicitly. Then we calculate the standard deviation, and this is basically the definition of the acquisition function, which is just UCB. And then we choose our next point as the argmax. So that's it. After that, we kind of do the housekeeping of storing the parameters, kind of get the predicted mean and STD, and basically update the training array. So everything else after this is the bookkeeping required to keep track of the objects which we measured, objects that we did not measure, and make sure that the measured is kind of shifted properly. So this is how the process runs. So it has been run for 100 steps. Then what we can do is just to visualize the results. So now interpretation of this data set is a little bit more complicated. So in this case, we have the measured points. These are the points that has been a part of the active learning process. So what I mean by that is that remember that we started with 10 seed points and we run the exploration for 100 steps. So this is the 110 run experiments. So for the measured points, we plot the predicted targets. So remember that we have clubs which should be 1, everything else should be 0. So these are the 120 out of 2000 cards that the algorithm explored. And these are the predictions, these are the ground truth labels. So in this part of the Latin space, we see clubs. Notice that the labels in this case are kind of deviate a little bit from 1 because the algorithm prediction is not, we don't make a, we don't use the 0, 1. We allow it to be either or, so that if we need, we can use something like softmax or whatever to make it rigid. But notice that nonetheless, clubs are all sitting in this part of the Latin space, and we see 3 groups of other types. So what are these 3 groups? I mean, the logical supposition is that these are 3 distinct labels, and these are 3 distinct labels. We can look at the ground truth labels for all points, and we can see that these are our clubs, and these are the other ones. So what else we are looking at? So these are measured points. These are unmeasured points. So unmeasured points basically form if we take all our data points, we take the model that has been trained on 120 only, and we use the model trained on 120 to make a predictions for all 2000 points. So this would be the output. And as you can imagine, all points are basically this plus this together. So since in this case we have much more points that were unmeasured compared to the points that has been measured, unmeasured and null points look almost the same. So look at the very interesting result. So compare the active learning result with the learning on the full data set. So when we learn on the full data set, we learn how to separate the clubs from everything else very well, but everything else kind of gets stuck together. Same time, if we try to do the active learning, so the algorithm learns the cards interactively, sort of constantly asking questions and getting the answers. So in this case, somehow it learned how to separate the all targets, so it no longer mixes the other three suits, but at the same time it did it based on the data only. So the ground truth, the predicted target for all of them is still close to zero. So the fact that we see the three different groups is because deep kernel learning, much like the VIE, will disentangle the representations of the data if it can. And in this case, the variability from the between the suits is strong enough that they actually got disentangled. We didn't ask it to do that, but it done it anyway. We can look at the behavior of other parameters like shear and rotations. So again, we don't expect them to be disentangled because we didn't ask the algorithm to do that. But it turns out that the property of the variational out encoder is to disentangle them anyway, and the DKL is sufficiently close to the VIEs that we can actually see this effect happening. Not super good, but you can clearly see that, for example, shear here changes along this direction. For this suit, it changes along this direction, and so on and so forth. So the interesting result here is that we compared three ways to explore this relationship between the card image, which is high-dimensional object, which is our molecular trajectory, whatever, and the way that our exploration models work. So for the autoencoders that's sensitive only to the data, we get something like this. So it's not really useful. We can clearly see that things change a lot. We will not be able to separate them without the ground truth. For the standard deep kernel learning, which is a supervised method, so in this case, we form the latent space that is very separate for the target versus the target that we're interested in versus other suits. At the same time, everything else got mixed. Practically, let's put it this way. Of course, for the supervised learning, we can also accomplish this type of thing using the classifier. But you can experiment that actually classifiers with their rotation objects don't have particularly good performance. They work, but not super good. But the deep kernel learning created the latent space, which is most expressive. So first of all, it accomplished the problem that we wanted, but it also separated other suits from each other and even to some extent disentangled the factor of variation inside the data. And what's really important is that not only it worked better, it also used a relatively small number of the examples. So here we used only 120 examples. For the supervised learning, we would use several thousand. Examples are days in the lab. So the fact that we are much more conscious in terms of how much data we use is actually superb. We can repeat the same type of experiment for any other suit. So we can write the same thing for spades. So in this case, this is how the full deep kernel learning works. So in this case, interestingly enough, all of them got disentangled. So these are spades. These are the two other groups. And this is how it will look like with the iterative process. So in this case, affect the latent space collapse. So you see that we have a linear manifold inside it, but it accomplishes the goal. It clearly separates our measured points from unmeasured. So in this case, this is the ground truth. So the spades are number one, they're here. Everything else goes kind of separated along this manifold. So if I wanted to avoid this problem, the way that I will deal with it is to introduce the larger number of the initial seed points. Then we will avoid the collapse of the data. But in this case, since I use only 10, it actually happened. Then I can do the same thing for the hearts. So this is the outcome. So now you can see that the hearts got separated. And I can run the same thing with the active learning. So again, hearts got separated. This is the ground truth. So they are a little bit overlapping with whatever is the number 3, but other than that, the task is accomplished. And just to make sure that things work, I can do it with the time-ons. Again, things work remarkably well. So this is the full supervised learning, and this is the active learning. Again, representation has collapsed. If we want to avoid it, we just increase the number of the initial points. So that was interesting, but basically what we try to do in this case is the sort of binary problem. We ascribe the function value of 1 for one of the hands and 0 for everything else. So we can, of course, kind of make it a more interesting function where we simply say that the label would be a 0 for one hand, 2 for another hand, 3 for the third one, and so on. So they all have different values. And again, it works remarkably well. So this is how it works for each hand being a value. So this is the predicted targets, 0, 1, 2, 3. This is the actual target, 0, 1, 2, 3. You see that this worked almost perfectly. And if we try to do it using the active learning, in this case, things becomes a little bit even more interesting, because you can see that we have clearly, using only 120 points, we actually learned how to separate the different suits. But what's interesting that in this case, it was clearly not enough examples. So this separation is actually incomplete. So if we try to run it for the full data set, you can see that this is our unmeasured points and their predictions, and this is our ground truth labels. So for training points, you can clearly see that this is suit number 1 and this is suit number 2. But the number of examples here, so for suit number 2, it's as you can see, this is just less than 10 examples. So 10 examples of one suit was not enough for the algorithm, and it really didn't learn how to separate these ones from this one. So 2 and 1 are not very well separated. If we take the trained model and apply it for the whole data, you can see that they kind of overlap with each other. So why is it happened? It happened because we got unlucky in our initial selection of the points. So we chose only 10. And you can see that for whatever reason, the algorithm spent most of the time exploring this particular value. So what is the reason? Remember that we defined our process to have the acquisition function being the UCB. UCB is the function that tries to maximize the function, of course, accounting for uncertainty, which basically means that our algorithm spend most of the time trying to explore the label that gives the 3 rather than other 2, because it's maximization algorithm. So unsurprisingly, it's end up exploring the third, the SU3, much more than we explored 1 and 2. Parenthetically, this is the reason why encoding the categorical variables by the numbers is not a terribly good idea, because practically there is no difference between what number we assign for specific suit. But if we use the optimization algorithm, then numbers matter. So that's kind of the reason why machine learning community has the best practices as it has now. But anyway, if we look at the shear and rotation, you can see that there is some disentanglement here and things are mixed. So clearly we want to have more high dimensional space than 2, but still. So this is the example of how we try to separate all the suits by the active learning. So what about the regression models? So imagine that we have all the cards, all 4 suits, but we want to learn the shear by looking at the image for all rotations and for all suits. We can do that for deep kernel learning as well. It's just that we are using now the function that builds a relationship between the image, so this 900 dimensional object, and the target, but now the target is chosen to be the shear of the data set. So let's see how it looks like. And lo and behold, this is how it looks when we train it on the full data set. So this is a supervised learning or regression, if you will. So we have all features, all targets. See what happens. So this is the distribution of the predicted target. This is the actual distribution of the shear in the latent space. So these are not exactly the same. So you see that there are some dark points here that are not captured here, but you can see that everything said and done, the distribution of shears and the predicted target is almost the same. That actually means that we trained a model that would work under the normal scenarios of the supervised learning. So if we set the the test set, it would work very, very well. So what else happens? Notice that if we say that we care about shear, but we don't care about the suit, it turns up that all the suits are distributions in the latent space are almost the same. So our function is trained in such a way as to ignore the specific suit of the card and learn only shear for each suit. That's actually super impressive. What about rotations? So rotations got partially disentangled. So as I constantly say, the deep kernel learning has elements of Gaussian processes and the variational autoencoder. So for the variables that it doesn't learn on, disentanglement works remarkably well. So what about active learning? So if we run the same type of analysis for the active learning, this is what we are going to have. So in this case, the latent space has collapsed, so we don't have enough example, and our rotation is too large. If I choose more examples, then it will work better. But by far and large, this is my predicted target. This is my, this actually shouldn't be class label. This should be a, where is it? No, this should be angles. This should be shear, and this is our prediction. So we should compare this thing, all points, to the shear in all points. In this case, it is not super good, but nonetheless, it worked to some way. So the reason why it didn't work particularly well is because our rotation disorder is too high and we didn't train it long enough. So you can see that from this example that if we trained considerably longer, then we will get the right answer. So going to the rotations, we can finally run the same thing for rotations as well. So in this case, our target is the angles. This is how it looks like if we do the supervised learning. So notice that if we try to do it in the supervised learning, that in this case, the distribution in the latent space and the general latent distribution is actually very complex. So as I said, this example with such a strong rotational disorder is actually a very challenging example for simple models if we try to fit everything in two-dimensional latent spaces. But you can see that this is our predicted target. This is our rotation target. So this is ground truth. They are close enough to each other. So you can see that there are differences, like these gradients are smooth because we use the GP sampling. Here they become a little bit more sharper, but nonetheless, these distribution look almost the same. If we do the active learning, then we get something like this. So this is our measured points. And again, remember that we run a optimization algorithm. So we try to focus on the points with the highest shear at the detriment of everything else. So our active learning algorithm is not pure discovery. It's an exploration exploitation, and it pays more attention to the maximization of the predicted target. If we wanted to run the pure exploration, we would have to use the acquisition function being just uncertainty rather than upper confidence bound. But nonetheless, what happens is that the approach is actually working. So we have the measured points here. This is what happens if we we train the model using only measured points. This is what happens if we take the trained model and apply it to the all points, so the unmeasured points and all points. And this is the ground truth labels. So the ground truth labels for the shear, it's mixed. Labels, it's mixed together. Shear, it mixed together. And the all points, the rotation. So in this case, the separation is not super good. But nonetheless, you can clearly see that we correctly identified the maximum of rotation over here. And generally, we are good when it comes to the minima. So they ended up being here, here, and here. This is not perfect, but remember that learning rotation from an object in the presence of the disorder is a complex task, and nonetheless, it works remarkably well. So going back to the presentation at this point, so this is the presentation. Apologize. Share screen. Going to the presentation. So these are the few examples similar to the one that have been in the notebook. So you're more than welcome to experiment with your own settings. So you have seen all of those. Question becomes, how can we make this work for the ferrosim? And the answer is that if we want to work it for ferrosim, we use exactly the same approach as we chosen for cards, except that instead of applying it to cards, we use it for the process trajectories inside the ferrosim as the input, and we apply it for the prediction of the ferrosim as the optimization function. So we have all trajectories available for the algorithms. We we calculate the ferrosim outputs for several trajectories. We train the model using these trajectories, and then we start to run this Bayesian active learning cycle. And this is how the output, so it's actually more time consuming, but this is how the outputs will look like. So if we train the ferrosim on the whole, and by the way, speaking about what we compare it with, let me show you the comparison. So remember that for using the VAE, our target functionality is distributed in the latent space of the VAE like this. So we are interested in the bright regions. We are not interested in the dark regions. Bright regions have a fairly complex structure, so BO works, but kind of more complicated. Compare this to the latent distribution that looks like this. So if we have access to the ground truth and we calculate this curls total as the function within the latent space of the DKL, if we train it on the full data, you can see that now the maxima are concentrated only in two locations. So these complex structures that we had, they, in the new encoding, become concentrated in a smaller number of regions, and these regions are localized. That means that it would be much easier to find them. So in this case, of course, it's a little bit of the moot point, because we train it on the ground truth data set. We already have all features and targets. But this is how it's going to work if we are doing it in the active learning scenario. So in the active learning scenario, this is the measured points. There are very few of them. These are all points. And then we can kind of compare it to the ground truth. And you can see that it's actually very, very close. So the process becomes much more efficient. And we can do it for other parameters. So we've done it for curl, but we can also do it for polarization. We can do it for whatever we're interested in. And the end result is actually really suggests that the deep kernel learning gives you a significant acceleration in how we can explore the complex phenomena in the complex parameter spaces. So this is the outcome for the classical VAE. So this is a VAE latent space, and then we can run beyond it. This is what happens if we have a ground truth for the DKL, so both trajectories and the functionalities. So now you can see that the structure of the latent space is much better defined. It's not super useful for us because we can get this latent space only if we run the experiments for each trajectory, so we didn't win anything. However, The deep kernel learning is active learning. So if we try to reconstruct this active process using a very small number of points, we can actually get the latent space, which is even better behaved. So the useful functionalities are sitting here. So what's the difference? The difference is that here we had to run the experiment, whatever, 10,000 times to get the ground truth for 100 by 100. If we try to get at the realistic Bayesian optimization, we still have to run a pretty good fraction of that simply because we need to discover these sharp features. So kernel has to be small, which basically means that instead of measuring 10,000 points, we need to measure, for example, more than 1,000 points in order to find it and have the kernel length being 3 pixels. If we run the active learning, we can have a much better behaved latent space, and we can run it using the just 100 points. So the gain is kind of very, very visible. So let's make a pause here. And do you have any questions about this part of the presentation?
Can I ask a question?
Sure.
So, how many data are needed to train a deep kernel learning model?
So that very much depends on the specific problem and the complexity of the input and output features. So for the time being, we know that as the rule of thumb, if we use a low dimensional encodings like 2 or 3 dimensions, and if our input data is relatively simple, like a process trajectories or image patches or whatever, then the gain is often compared to classical Bayesian optimization, the gain can easily be a factor of 1,000, oh sorry, factor of 100. So we need 100 times less training data. How this will generalize for other applications and other dimensionalities of data, we don't know. So that's can be done only by trial and error, and you need to experiment. But generally, I'll show you the examples of it on the examples of it on Monday. We probably wouldn't get to it today. But generally, our experience was that for most practical problems with the complex feature spaces, like images, process trajectories, whatever, using Bayesian optimization compared to the human choosing the parameters does not give us much advantage. Use of the DKL makes a difference. Like it makes a real difference. It's just that some things become possible that did not make any sense before. As I said, caveat is that for each application, it's necessary to apply it, and then you kind of learn how it works. How much acceleration does it give you?
Thank you.
So now let me show you another example. So notice that how we can use the DKL to explore the complex chemical spaces. And of course, if we explore chemical space, that means that we can explore compositional spaces, microstructural spaces, and so on and so forth. So ultimately, this type of objects are the same. So another very important thing is that notice that I'm not a theorist, which basically means that that's working with the theoretical data and prediction is not something that I do every day or do regularly at all. The important thing, reason I'm showing this example is, first of all, because it's a good example to show how the deep kernel learning works on complex objects like molecules. And secondly, to illustrate that the activation barrier for learning these technologies and applying them for new and complex problems by now is actually very, very low. So let me show you how we apply the deep kernel learning for molecular discovery. So here the basic elements is that we are using the QM9 dataset. So QM9 dataset is one of the standard and by now fairly old dataset of the molecular properties. So basically it encodes the molecular structure and it encodes some molecular properties like enthalpy, like dipole moment, what's not. So I provide the links for the original data set and therefore the information of what is there using to this original website Quantum Machine. So this notebook has several parts, kind of including how we create the encoding made by some of my colleagues. But let me just guide you through it step by step. So where do we start? So we start with installing two useful libraries. One is called RDKit. So RDKit is basically one of the oldest libraries and well-maintained libraries in Python that allows us to work with the molecular structures. So Selfies is the relatively new library, which was invented only 3 years ago by Mario Kren, which basically allows us to work with a subspecific form of how this molecular structure can be represented. So molecules is obviously a complex object, so Selfies is one way how the molecule can be represented as a string. So then we include some support functions, so there is nothing particularly useful here except for RDKit and Selfies. So we define several parser functions, so they allow us to parse the data coming from the RDKit. And then what we are going to do is to download this QM dataset. So I created a local copy for that, but this gdown should work. You just, if you run this code, it will download the copy of the dataset to your cloud space, and you will see it. And you will see it here. So what's inside this dataset? Inside there are molecules. So if you unzip it or untar it, whatever, you're going to have access to the large number of the files having the molecule descriptors. In fact, there would be something like 140,000 of them. So Colab has limited memory, so we cannot run the analysis on all 140,000. So it seems like the limit for Colab Pro is Pro Plus is 10,000. If your code crashes with this notebook, just make this 1,000 rather than 10,000 or 2,000. So then you will be okay. So once we downloaded these data sets, what we do is we basically parse it. So we create some empty list for the smiles representation, the original for the kit, for the QM9 enthalpy, dipole moment, and so on and so forth. And then basically what we do is we parse, actually it's even 5,000 here. We parse through our data and we create a list with the smiles. So smiles is another form of molecular description. And then the molecule parameters. So enthalpy, dipole moment, HOMO, LUMO, gap, whatever. So then we have the list of those parameters. Once we've done it, we basically have this access to this feature. So for each molecule, we will have molecular weight, polar area, logarithm of solubility, hydrogen bond donors. So these are the type of descriptors that organic chemists like. And at this moment, you can kind of have the feeling that we are very similar, have a very similar situation as we did with our cards example. So remember, when we have the cards, we had a card as an image, and then we had a problem where we tried to calculate the suit of the card or rotation or shear from image directly. So the point where we can try to calculate the molecular weight or any of these parameters from the molecular descriptor is absolutely the same problem. So from the point of view of machine learning, there is absolutely no difference between the problem of analyzing cards and analyzing the molecules. So that's exactly what we do. So after we run all this parsing, our output would be a table of the 5,000 entries where we have the molecules. So these are described through the smiles vector. And then we have this molecule parameters. So kind of those of you that are familiar with the organic chemistry will recognize all of them. Those of you that are less familiar can realize some of them, but basically these are just numerical parameters: partial charge, dipole moment, enthalpy, so molecular weight, and so on and so forth. So this defines our task for the deep kernel learning. So this is our input space, molecules. This is our targets, so any of those parameters. Can deep kernel learning help us do that? Yes, so this is a small, for the convenience, we convert the selfies representation, sorry, smiles representation into selfies representations. So this is how it is done. It's just one encoder function. The caveat is that sometimes the expressive power of selfies for the time being is smaller than smiles, because this is a relatively new library. So basically all I did is to reject small number of molecules that don't fit in the current constraints. And it turns out that there are a few molecules which cannot be represented through the current version of the selfies, and these are the molecules where have the nitrogen with the 5 bonds. So for whatever reason, they don't like nitrate, but we just remove 5 out of 500. So, and then we have our filter table, which now is correct. So notice that the numbers remain the way they are, so we don't shift the numeration. So what we do with that is we generate one hot encoding. So what does that mean? It means that in principle, we can create the DKL that uses the smiles, that uses the, sorry, there should be smiles vector as an input. Practically, this is not super convenient for us because that's not we will have to rewrite all the network. So what we are going to do is to basically represent our molecule through the one hot encoding of the structural elements. So if it has the alkyne chain, that's one element. If it has a ring, it's another element. If it has NH2 group, then it would be a third element. And then this part of the space is basically the empty slots if the molecule has been small enough. So basically, this looks like a barcode that you will or QR code that you will typically see everywhere. In fact, it is a QR code for the molecule. So the important thing to know is that for each molecule, there would be only a QR code, and for one QR code, for each QR code, there would be only one molecule. So you can go forward and backward from this to the molecule any way you want. So that's all we need from them. So let's see how this type of systems behave. So remember, we started with the cards example when we took the cards and then we calculated the variational autoencoder, and then we looked at the distribution of the ground truth labels in the Latin space. We can do exactly the same thing for the molecules. So notice that in this case, I wrote a very simple autoencoder that basically takes this type of, it's not even anything packaged, it's just a very simple autoencoder written in Keras. So I encode my data and then I train the autoencoder. So this is how the Latin space looks like. This is how the distribution of the properties in the Latin space look like. So what should you be looking at? So first of all, look at the structure of the Latin distribution. So you see that there is a fairly complicated structure. That actually makes sense because molecules have repeated elements, and they form the groups where these repeated elements are maximized. So you can see that if I use as one of the parameters the ring count, you can clearly see that the ring count is one of the primary factors of variation. So the ring count is distributed in some way that makes sense across the Latin space. That being said, if I look at other ground truth parameters, I don't see much. So I can kind of say that, okay, enthalpy is going in the opposite direction. So it's kind of anti-correlated in some sense with the ring count. Everything else is pretty weird. So molecular weight forms some groups, but clearly that's not the primary factor of variation. Things like a partial charge or the dipole moment, they are distributed absolutely randomly. We don't see particular order here. So why is it happening? It's happening because molecule is very complex. So if you look at our descriptors that we've chosen for the molecule, it's actually very high dimensional descriptors that has a lot of elements. And it has a very high dimensionality. So it's whatever, 28 by 30 in this case. Once we take these descriptors and we project them encode them in the latent space of the autoencoder, we go from a high number of dimensions, all of which matter, to only 2. So we cannot expect that the quality of the reconstruction is particularly good. And we also know that the quality of the reconstruction is not particularly good, simply because our latent space is kind of not very expressive. There is a very significant reconstruction loss when we've done that. So the fact that we see some variation in the ring count across the latent space is already very impressive. But clearly, if we tried to build a regressor, meaning we try to use the latent variables to predict any of these properties, we would fail rather miserably. Why do we say that? We say that because we have access to the ground truth, and there is nothing in this data, in the way this data look like, that will tell us that the regression would be successful. Of course, we can do it better by building a more expressive autoencoder using high dimensional latent space and so on. But let's compare apples to apples. So we compare one type of apples is the VAE with the 2D latent space, and another is DeepKL with the 2D latent space. So let's see how it works. So we start with the same example as we did with the cards, where we basically said that, you know what, let's start with the certain training on the full data set and just see how the latent space and latent space features will be demonstrated. Lo and behold, see what happens. So in this case, of course, when we train it, we need to define the target, right? And we define the target to be the dipole moment. If we try to visualize the dipole moment in the latent space of the autoencoder, 2D latent space of autoencoder, we get something like this. It's not particularly interesting. It's almost featureless. But if we try to do the same thing using the deep kernel learning, see what happens. You can clearly see that we get the output to the actual labels. We get the output to the predicted targets. So the actual labels and the dipole moment is the same thing. So you don't expect to see any difference between these two. And this is another label like a log P. So see what happens. We constructed the latent space in such a way that it builds the best relationship between the molecular structure and the dipole moment. Once we've done that, you can see that each molecule that has a strong dipole moment basically formed an area around itself where the dipole moments are also large. So like this one has the molecules with a large dipole moment. This one has the molecule with the large dipole moments, but notice that it is surrounded by the empty space. So why is it happening? It happens because the structure of this molecule is such that it is fairly unusual. It's very different from anything else. So in some sense, it's an outlier. And because it is an outlier, it is surrounded by a fairly large gap. But nonetheless, the molecules that are close to it still have a large dipole moment and have some similarity in terms of the structure. So this molecule is also, 3 molecules are also outliers. These several molecules are outlier. But nonetheless, you can immediately see that the structure of the latent space become much more ordered and much more kind of easy to decipher by the human eye. And the thing that I find perfectly amazing is that this is just a 2-dimensional latent space. We try to encode the structure of the molecule by 2 latent variables only. It's actually a very tall order. So that was really, really impressive. That's actually the true power of the deep kernel learning. So we can experiment further with this type of thing. So for example, we can compare the prediction and calculate the error. So error is simply actual target minus the predicted mean. So that worked remarkably well. We can look at the uncertainty, and these are the results. So this is what we predict. This is the error. It's actually reasonably small. This is the uncertainty. So you can see that prediction is actually very certain in the center of the Latin space, and there are uncertainties on the periphery. But by far and large, we kind of get an idea of how well the DKL worked. And the next step that we can do is, the obvious question is, do we know what these molecules are? And, since we have the initial data set, all we have to do is to use very simple function to find the 5 maxima. And so we tell our code to find these molecules. And once they are found, we can ask it to decode those values. And you can see that these molecules kind of look like that they should have a very high dipole moments, because generally all of them have a positive group on the one end, a negative group on the other end, and the large distance between the two. So that's where the large dipole moments are coming from. So in some sense, going back to our original attempt to do the same thing with the autoencoder, this is what our encoder gives us. No prediction, no structure, just kind of a mess. And this is what the deep kernel learning gives us. So the deep kernel learning gives us these Latin spaces, which are much better ordered. So you can say that, okay, maybe we can want to find out what happens in these groups. It's not terribly difficult to analyze this, to write the analysis function that will pick the points in the Latin space which are sufficiently far from each other. And this is what we get here. So then we made sure that we pick the separate structural classes. So each of these bright dots is a specific structural class of the molecule. So the molecules that are close to each other have comparable dipole moments and comparable structures. Those that are far from each other have large dipole moments, but different structures. And you can see what are these classes are. We can run the same type of things to find the molecules close to that, but that's already kind of straightforward. Since we have access to everything that goes on the Latin space, it works. So then let's see what will happen if we run the same thing as the active learning. So if we want to run it as let me go back to the beginning. If we want to run it to the active learning, we use exactly the same principle as we did with the cards. We start with our encodings, we choose our target, we choose the number of initial steps and exploratory steps. So this is kind of 200 seeds, 200 exploration. We define the same type of exploratory loop. We use exactly the same type of the objective function. So this is a UCB. So we want to find the regions where the dipole moment is large. And then if we run it, then we have our representation of the space with the measured points. So these are the points that has been explored by the active learning. These are the all points. So we train the model using the measured points, and these are the all ones. These are the encoding of the unmeasured points. This is the ground truth. So did it work particularly well? Well, yes and no. It clearly have found the points with a strong dipole moment here and here. I suspect that once we did it, we essentially found that maxima corresponding to one of those structural classes, and we spend most of the time exploring this structural class. That's actually the reason why exploring molecular spaces is complicated, because if we target specific functionality, there are multiple molecules that will have this functionality. They can be very different structurally, and that means that the algorithm that locks on one type of structure in order to get this functionality will ignore others. So we always need to balance the exploration and exploitation in order to find the new classes, and exploitation in order to get to the right maximum within the class. But nonetheless, it actually worked reasonably well. At least we found one group. So this is our exploration path. So this is how it goes on. And we can get the kind of sequence of molecules that we were probing across this path. So if you were running this type of notebook as the way to guide your research in the lab, you would be following this type of exploratory activity. So if you're curious, you can explore the same type of behavior in high-dimensional spaces. So I made the example for 5D. And interestingly, the natural question becomes, can I buy this type of stuff? So it's a little bit more complicated than the theoretical data sets, but basically by now there are the public databases that allow you to figure out whether the reagent can be procured or not. So for example, I didn't fully finish it because I just explored whether it is possible or not. But generally, if you look for specific material compound, you can find out whether it is available or not. So in some sense, whether you can buy it or not as well. So this is what I wanted to show about how DKL works for the molecular discovery. So any questions about this part? Okay, if not, then let me show you one more thing about how we can use the deep kernel learning for the active experiment. And let me switch back to the presentation, and I'll start with the defining the problem, and then we will kind of go through the definition of the problem through the several examples how it worked, and then on Monday we are going to go through the notebook and discuss the human in the loop interactions. So the last example of the deep kernel learning after the cards and molecules is the example of the physical discovery in the active experiment. So imagine that you are running either the electron microscope, or you're running the scanning probe microscope, or you're running the non-indenter, where you also have the optical imaging or SEM, or any other tool where you have access to the general image, which shows you some details. And then you can one by one do the more expensive precise measurements like indentation or other spectroscopy. So this is a very, very common setting for the physical labs, and people who do microscopy do it all the time. People who do other type of experiments encounter it fairly obvious. So imagine that we have access to for simplicity, let's assume that we have access to the structural image, and we have access to the physical feature to some sort of spectrum. So as I said, structural image can be optical, can be electron microscopic, can be whatever. Behavior of image interest in the spectral image can be non-indentation, can be stem mills, can be 4D stem, and so on and so forth. So actually, this may be even a better example for that. So, and all imaging methods have that. So the question becomes, how can I use machine learning in order to automate this process? So one way I can do that, and that's what humans can do as well, is to have a look at the structural image, identify the interesting features here. So this is the structural image of the scanning tunneling microscopy of the some high temperature superconductors. So you see the beautiful dopant atoms, you can see some surface reconstructions, and then you can say, look, I want to take spectra on these bright atoms, or as it may be in this case, in these dark spots. If you make measurements in these 3 or 4 dark spots and all the measurements would be the same, you're going to say that, you know what, by now I understand what is the characteristic spectra of these spots. So I can choose the next target. For example, this one. Here the spectrum will look like this. Then I will explore several other spots like this and say, you know what, I have a good enough idea about how they behave. I really don't need to take the measurement in any other of those. And then I will choose the next target. This is the type of experiment that humans are very good at. And this is a type of experiment that is very easy to automatize using the machine learning. So if we have access to the instrument control, finding that if a human can identify the interesting object, then at the very least, using human labeled data, we can train the machine learning, the neural network, to identify all the same objects automatically. Very often it can be done even easier than using the neural networks. So in something like this, I will simply use the finding maximum filter, but neural network in this case is the ultimate solution. So if human can do it, neural network can do that, as simple as that. But there is an opposite problem. Imagine that now, rather than finding the spectra corresponding to certain features, I want to solve the inverse problem, which means that there is something in the spectrum that I'm interested in. And I want to run the experiment when I find which of the element of the microstructure will actually maximize this property. How can I do that? So the simplest way to do that is to define a rectangular grid. So if you don't know anything like Jon Snow, do everything, I guess also like Jon Snow. Then we define the rectangular grid, and we do measurements everywhere on this rectangular grid. So why is it a bad idea? First of all, it's not a bad idea. That's how things are done everywhere now. But this is a very expensive idea. So taking the measurements everywhere takes time. And in most instruments, time costs money, but also long measurements are associated with the damage for the sample or damage to the probe. So our experimental budgets are limited, and also our stability of the instrument and the sample are also limited. So a second problem is that very often we have objects where some features are sharp and some features are kind of much larger. So if we do the sampling on the rectangular grid, there is no guarantee that we will sample the points that hit the objects of interest. We can, of course, fight with that by taking the measurements over the very dense grid, but then our measurement time grow, and they grow up, they increase as a square of the number of points in the grid. So it's very time consuming. So it turns out that this process of finding the objects that have the physical behavior of interest, that's exactly the problem or that deep kernel learning can solve. So very much like deep kernel learning worked exactly well to find the suit or the rotation angle in card, or it worked very well to find the properties of the molecule, it can be run in order to find what microstructural element maximizes certain behavior in the spectrum. How are we going to do that? So there are several steps for the process, and I'm going to guide you through those step by step using the example of the electron microscopy, or at least for today, electron microscopy. So what we start with is we start with the full image. So we have access to it even before we start the experiment. Then what we do is we take this image and split it in the collection of patches. So we assume that the structure property relationships are local, which basically means that the property of the spectrum, specific spectrum, is controlled by the local properties, but not by the properties of something very far apart. So notice that it's not always true. There are always exceptions, but in the vast majority of materials, it is the case. So then what we need to do is we need to define what we call a scalarizer. So most instruments give us access to some form of spectrum. We need to define what is about the spectrum that we're interested in. So in molecular example, we said that we are interested in the dipole moment or, for example, the molecular weight. In case of the cards, we were interested in rotation or shear. So in those cases, these are scalar properties, but the instruments typically give us spectrum And we need to say what's about the spectra is important. So the simpler way to derive the scalarizer is to say that we want to have the intensity or position of the certain spectral feature. Or we can make a more complex scalarizer. For example, we can feed the spectrum by the two peaks, and then they take the ratio of those peaks. If our data is more complex, like something like a diffraction pattern, we can define scalarizer in any way. It can be fitting the disks and finding the center of mass. It can be sending the data to some form of the physics-based reconstruction and use that output. The important thing is that all the scalarizer has to do is to take the spectral data as an input and provide the measure of the physical interest. So how interested we will be in this particular spectrum. So notice that strictly speaking, scalarizer doesn't have to be physics-based. I can also take the multiple examples of the data, ask human operators to tell me whether this data is interesting or not, and then train a neural network classifier that will take any data set and say interesting, not interesting. So it's that broad. This being said, it is not broader and not terribly different from how humans examine the data. So if you present the data to the human expert can tell you this is trivial and this is not trivial. So basically a scalarizer just tries to put the value on that. So how do we run the deep kernel learning experiment? Very simple. Imagine that this is our image plane. We already have access to the whole imaging information. What we do is we run the spectral measurements at several seed locations. So much like we did it with the cards and with the molecules, we select several seed locations to get the initial idea of how the data look like. And in those selected locations, we measure our spectrum. Once we've done that, we can calculate our scalarizers in all those locations. So not the full spectrum, but just the scalarizer. And then we train our deep kernel learning model. So we have the inputs, which are the patches at the locations where we taken the measurements. We have the targets, which is the scalarizer value at the locations where we took the measurements. We have a deep kernel learning workflow that learns how to predict this one-dimensional targets from the high-dimensional inputs. Exactly the same way as we did it for the cards and molecules. And then you can predict what we are going to do after that. So after we train the deep kernel learning model, what we are going to do is we are going to apply it to the full data set. So remember that we have structural data everywhere within the image. It's just image patches. We have access to the scalarizers only at some number of locations. What we do is we take all structural data, apply it, use the trained model on this data, and the trained model will give us as a prediction the expected value of the scalarizer and expected value of the uncertainty for the scalarizer. So in other words, this is the moment where you can make connection between the way the Gaussian process works and the automated experiment. We deal with the fact that deep kernel learning can predict the values of scalarizer for the regions where the measurements cannot be taken. It can predict the values of the uncertainty of the scalarizers for the regions when the values have not been taken. If we have the prediction and uncertainty, we can combine them into the acquisition function. And once we combine it in the acquisition function, we start our myopic optimization loop. We choose the next location for measurement as the maximum of the acquisition function. We do the measurement here, and that's how the deep kernel learning active learning works. We acquire structural data, we measure the spectrum, we define what physics we are interested in, so what we care about. Based on this, we define a scalarizer, we train the DKL model, we define our policy, so how we value exploration versus exploitation, exactly the same way as the Gaussian process. We decide the next position, and then we repeat this process. So let me show you how it looks like. So this is the example of the yields measurements in electron microscope on some two-dimensional materials, manganese PS3. So we can, these are the examples of the yields measurements at two locations. So we can define the scalarizer here. So in this case, we say that, you know what, we are interested in the behavior of the edge plasmons. So this is our yield spectrum. This is the bulk plasmon. This is the edge plasmon. So what we want to do is to find the regions where the ratio of this peak intensity to this peak intensity is highest. So all we have to do is to take the spectrum, fit it by two peaks, take the ratio. This becomes our scalarizer. That's what we give to the deep kernel learning algorithm in order to maximize. So this is how, what you're going to see here, this is not a simulation. So this is actually data from the actual microscope. So this is the electron microscope image. This is our acquisition function. The red dots are the locations where the initial measurements has been taken. So these are seed locations. And this is how the active experiment learns. So you see that the instrument starts to explore our material, and you can see that the measurements are being done at the locations when there are edges. So our algorithm tells the instrument to do measurements at the edges, and it finds the edges following this criteria. So that was actually very interesting, because we essentially took the electron microscope, we deployed the machine learning algorithm on top of this microscope, and then it started to explore our system. So again, the algorithm that we have been used is DKL, and except that in this case, this is our input data structural. And these are several more examples of how this experiment would run. So for this particular flake, you can see that it explored this edge. For this particular flake, that is the one that you have seen on the image, it has explored this edge. For this flake, it kind of was unclear what type of edge it is more interested in, so it was sort of fluctuating around it. But generally, it was exploring the edge and not everything else. For this flake, it explored this edge, but not this one. And in principle, it worked. So that's an example of how we can run the active learning. And I showed you for yields measurement. We can do the same thing for more complex measurements like a 4D step. So the same principle, we define our object, we define the parameters we are looking at, we define our policy, how we want to balance exploration exploitation, and again, we have the access to the forward and inverse experiment. Forward experiment when we know the objects of interest in the beginning. So then we can use the some form of the deep convolutional network to identify the objects and then do the measurement that we want or the object that we want. That's relatively straightforward. Or we can use exactly the same deep kernel learning based Bayesian optimization, but now we measure ronchogram, meaning our 4D spectrum, define the scalarizer, train the DKL, and repeat the process. So these are the few examples where we've done it on the pre-acquired data, so you can always fine-tune the process, and you see how the acquisition function, prediction, and uncertainty evolve. So this is the example of the acquisition function, prediction, uncertainty when we use scalarizer as the angle. Another is when we use the magnitude. And the dots that appear on these images are their simulated exploration trajectories. So here you will notice one red flag, or potentially red flag, and we are going to talk about it more on Wednesday. You will see that there is some healthy exploration of our material in all cases, but you can also see that in some cases, some points are explored more than others. So in this case, this is this part of material. In this case, this is this part of material and this center of the hole. Why is it happening? It's happening because remember that I said that in one of the first lectures that the optimizations algorithms can get stuck in the local potential minima. And that's exactly what happens here. So we cannot control our space very well because this is a very high dimensional space. But the phenomenon of getting stuck in some minima is real in any case. So that being said, you can say, okay, maybe this happens only on the simulate data. Absolutely not. So this is the example of the active microscope when we run the experiment on the active microscope, and you can see that eventually we have discovered this region. Maybe it is the region where the useful properties are, or maybe this is where we are stuck. So on the next lecture, which would be on Monday, I'm going to illustrate more how the deep kernel learning on the active tools work. And I'm going to illustrate how we can transition from the standard deep kernel learning to the scenarios when we have human in the loop active learning, meaning that the human actually controls monitors the process and intervenes with that. So let me stop at this point and let me know if you have any questions.